Okay, so last week we had a brief introduction of the agents from artificial intelligence view. If you have any question in that term, you can feel free to ask. All right, good. Today, formally, we are going to start the course, reinforcement learning, and today's course is crucial and very important because we are going to know some basic understanding of reinforcement learning. Although they are simple, but they are playing vital role in reinforcement learning. The terms that we are going to talk about today forever will stay with you as long as you're doing something with reinforcement learning. Because of that, be careful to know, for example, what's the value function, what's the estimation of the return, and I will introduce I will introduce these topics for you and discuss what are them in detail, so that later always we are going to use them. Also in literature, if you already studied or you're going to study, you will see some confusing terms that are going to use. I'm trying to introduce them at the beginning to you to clarify everything in your mind so that you can understand whole course better. So we have reinforcement learning, and the topics that we are going to discuss, as I mentioned, introduction to reinforcement learning first. Then we talk about the multi-arm bandit as simple and the basic entrance of the reinforcement learning. We will see what is it. Then we talk about the Markov decision processes, and we will see some algorithms based off the Markov decision processes like value iteration. We will see the policy iteration and a couple of more algorithms there. Then we will go into the Monte Carlo algorithms. We will see three different kinds of algorithms with Monte Carlo. So after Monte Carlo, we will see we have some challenge problems here. We move to temporal differences algorithms, TD evaluation, and how those kind of class of algorithms are working. Of course, there are hundreds of different algorithms here. We just introduced the most important one. You get the most important clue what's happening there. Then later, if you study the other ones, you just can understand better. We will see the most important algorithm in reinforcement learning, Q-learning. That's the key algorithm that kind of changed many things in reinforcement learning and machine learning. Then we talk about SARSA, extended SARSA, and we will have introduction to the deep reinforcement learning. If you already studied, when I get to that point, I will ask questions to see how many of you guys know about the neural network and deep learning. If you know them in advance, that's easier for you and for me. I can quickly go to cover more topics. But if you don't know those topics, we have to review and give you how they are working. Then that makes it a little bit slows us down there. But anyway, after having introduction there, we talk about the policy gradient, actor critic, and state-of-the-art algorithms that nowadays are working and they have pretty decent results. Any question about here? And of course, if you have time, we will cover much more here. There are a couple of important algorithms. I will be happy to tell you what's going on there. These topics we already talked, and the books that you can study yourself. And this is the reinforcement learning and introduction. That is the critical book that we are going to dive in. And most of the topics that we have is here. But the writer of the book also is suggested that this book usually should be teaching in 2 semesters, not 1. But for sure, I will try to go the important parts to cover much more deep learning based algorithms. Because nowadays, if you want to solve really problems that are existing in real environment, we have to move a little bit faster to the advanced algorithms. Otherwise, real applications, if you're like kind of person that you go search on the internet, watch YouTube, you see reinforcement learning, they are doing a stunning job, and you're interested in do the same thing. But to be able to do those fancy algorithms, you need to know what's happening in background. Otherwise, it will be shallow, just running example that everybody can do. You need to know the underlying structure. That in this course, I will try to do that. But as far as we can go, we move toward the advanced algorithms. So like if you knew the basics, I would like directly go there. That would be also very nice. But anyway, I will try to make balance over there so that everybody can use the course well. So in chapter 1, we are going to talk about the introduction to reinforcement learning. We will talk about the brief history of reinforcement learning, where it is coming from. We will talk about the differences of the reinforcement learning and machine learning techniques, if you are familiar with. We talked a little bit about the artificial intelligence, but we need to also clarify machine learning. We will see some small application examples. I will clarify for you that kind of reinforcement learning is very interesting and applicable in very interesting applications. And when the time gets, we get to the time that I can show you advanced techniques, then you will see that kind of future goes toward reinforcement learning and learning-based techniques that even NVIDIA nowadays with the RTX GPUs are specifically designing hardwares to do this. And I will share you later some videos that you can see how important it is. Of course, here also today we will try to have formal presentation of the fundamentals. I will try to formulate them in simple equations that we are going to use them later in our reinforcement learning algorithms in detail. So we will have some formal presentation of fundamentals. So the objective here is discuss basically importance of the reinforcement learning and understand the basic elements that we have. So briefly we can say reinforcement learning is the science of the decision making. So think about it. Decision making. We want to have agent that we briefly introduced last week that wants to make decisions, and reinforcement learning is trying to help us to make decisions. And it works for all kinds of problems, games where decision sequences are important. I decided to come from there to here. Why? This is a decision. So you decide to sit here. This is a decision. This can be expanded to any problem that we have. Anywhere we want to have decision. So, for example, we have chess. Of course, every time we have decisions to make. If you cannot see, you can change your seat because I usually stay here in this corner. If you have problem, you can change. So we have the chess game. You are all familiar with chess. Reinforcement learning can play chess. Maze game, that robot needs to solve a problem like that. That always is decision, right? Robot should say, turn left, turn right. Which direction I should choose. Then path planning. Something similar to maze, but kind of different. The maze is the sub-problem of the path planning. Industrial robot arm. You have industrial robot, and this is very common to use reinforcement learning that need to grasp an object. You need to do the pickup and placement procedure. Need to run very complex motion planning of achieving some endpoint by robot's end effector, how to plan to go there, generate trajectory. All those are decision making for industrial robot arms. I can state more than 10, 20 different applications that they are diverse and well-known field of study for industrial robot arms that you can use reinforcement learning in order to deal with this problem. I will show you visual examples, I will show you codes, examples, and the simulation environments that you can go do all these jobs. There are also some pre-designed environments for you guys in the reinforcement learning platform that you can directly go control them. We will discuss it when time comes. We can have different kinds of robots. For example, a scooter robot, a robot that needs to This is soccer robot, not a scooter. Soccer robot, we have the sweeper robot that needs to clean the environment, and I can say all kind of robots in different perspectives can be used in reinforcement learning, because we always have decision making for reinforcement learning as an important part. And we may do not have complete model of the environment and state transition. I will clarify soon what is this state transition. But if we don't have model of environment, means that we don't have the map, we don't know how the environment is reacting to us, how the environment may respond to our agent. So reinforcement learning is trying to solve it. At first, of course, we will start to understand reinforcement learning in this course by model. And also we have model-based techniques. I will clarify for you soon everything. Then you will see that, okay, if you don't have even models, no idea of how environment can react. If I punch this guy, what will happen? So these are nice applications. If we don't know, our agent as reinforcement learning learner is going to learn it. So, for example, last time we talked about agent. I'm not going to explain anymore. And today we are going to talk about more than 20 different new topics. I'm not going to explain them in future repetitively. Because of that, be careful to memorize them and understand what's happening there, that later when the problems becomes complex or we're gonna solve something, I repetitively use those terms. Please, also if you have questions, you can ask. So reinforcement learning has tremendous popularity in last decade, and you will see how also with the examples. So specifically last week we talked about the agent. What is the agent? We have this guy as agent, can be robot, can be a small programming computer, can be human, whatever it is. It can be agent that can do action in the environment and sense the environment. Do action. Where is the environment? Whole Earth can be environment, whatever it is. Universe can be environment, wherever it is. It can be a robot that is like Robonaut 5 from NASA that is going to do some missions in space, or anything. And there are some feedbacks to our agent. So not only we are limited to we are not limited to physical environment. That can be also simulation. That can be a game. So that reinforcement learning also is kind of get famous with solving those kind of games. At the beginning stage, when reinforcement learning got also very famous, there were two stages. The second one was when it was able to play games. All the Atari games now, reinforcement learning can play better than best human ever can do. If you're a good gamer, you're claiming, go compete against reinforcement learning. So we say the agent learns how to move from initial state to goal state. What was this state? What was the state space? We discussed it. So all possibilities of the environment is called the state space that can be discretized and can be stochastic and deterministic. We discussed about this. An agent can start from initial state, one of all those possibilities, and move to next state. So that's called initial and goal state or target state. And our agent always asks question from himself, what is the best action at each independent state that I am. Always keeps asking, okay, what to do now? Then moves to here, what to do now? Move somewhere else, what to do now if you have a robot that moves in the environment. And for sure, we have challenge of the dynamic nature of the environment. Inevitable to deal with it. Maybe we simplify in some problems, somehow try to simplify to understand what's happening, but the dynamicity is in the nature of the environment, that reinforcement learning tries to learn that dynamicity also directly. How? We will see. So reinforcement learning is useful, of course, in many different applications. We will have a couple of examples today. For example, when we are talking about which action to do, you can imagine there is a helicopter that is unmanned, and reinforcement learning controller learner will try to learn how to control it. So think about it. What is the agent here? The agent is helicopter. What is the action that we can do? All the possible balance control. If we can, there can be, depending on us, we can define the control can be directly the actuators, two motors, speed, right? Or can be like, we can say, okay, let's discretize it, and the angle of robot, tilt left, right, forward, like rule pitch, left, right, and if go up, go down, we can discretize the action space like that. To rotate to the left, rotate to the right, etc. So the question is reinforcement learning able to control it, do you think? Is it? Yes or no? Who says yes? Raise hand. You say yes. Everybody else no? I ask that question again. Does reinforcement learning, so up to date, is able to control this helicopter completely autonomous or no? Who says yes? Raise hand. That's okay. That's too low. Of course it is. I'm telling you, reinforcement learning is now very famous, can do everything. Now even not only control, it can do flip better than human. Just Google it. You will see lots of videos on YouTube. The motions that human cannot do with joystick, the reinforcement learning can do. Very nice robotic applications. Plus we have algorithmic or agent-based kind of the parts that works in virtual environment. For example, let's talk about the resource allocation of the operating system. I don't know how familiar you are with. Now we have CPUs, and we have hundreds of threads maybe are open in our computer. Threads means lines of code that simultaneously working inside your computer. And who is going to use the CPU and resources first? There are different techniques in operating system course. You may study like FIFO, first in, first out. If you have 100 processes, who comes first, that serves first, uses the CPU. But this has lots of problems. We have over 20, 30 different algorithms that improves this FIFO, first in, first out. Then we get to the point that still those kind of algorithms in very dynamic environment are not performing well. Then these kind of resource allocations can help us in computer systems. You may say, okay, one computer system is working, Windows is working very, very well. You're right, but if you have data center, if you have thousands of those computers working together to solve problems, we have then load problem, request problem, energy usage consumption problem. So managing all of those in real time requires decision making, and those decision making can come from reinforcement learning. You can Google to see, study if you are interested in each one of these that I'm going to introduce to you as applications of the reinforcement learning. Let's see one video, very simple example. But this is old. This is not state of the art at all. I just want to, for now, we will see the state of the arts also, but let's have a look. We have a robot, industrial arm, not that fancy one also, that is going to try to learn the flipping of the kind of food. So this is the reinforcement learning. At the beginning, tries. So you see after 3 trials, after 10, still no. Stupid. But after learning. The interesting point here is that, okay, robot was able to do the same procedure by learning after, for example, here 50 trials, but of course, depending on what you're doing, maybe take 500, 5,000. The interesting thing is that you will see, don't tell robot anything that what the robot is doing and how to do that. We can say nothing to the robot, zero information, just we can say if you could do that or not, success or fail. Just the feedback can be to the robot, success or fail. Robot will learn it. To flip the, for example, food, pancake or whatever it is. So let's have a look at the history of the reinforcement learning quickly. There were 3 concurrent threads that they were evaluating, evolving together. First, learning by trial and error. So it was kind of like you let the agent try whatever agent wants and learn from trying. It originated from physiology of the animal learning. Animals also doing trial and error during learning time, and earliest work in AI resulted this stage of the reinforcement learning started early in 1980s. So at the beginning we didn't have reinforcement learning, just we had artificial intelligence that finally in some certain point we achieved to reach here. I showed last week a little bit of what was happening by demonstrating the agents. Second one was that concurrently but separate from the first stage was developing was the problem of the optimal control and its solution using dynamic programming. So you may have no ideas what's the optimal control and dynamic programming. In next slide I will explain. The research in optimal control also began in 1950s. So apart from second one, we have third one. That third one was temporal differences learning that inspired from the mathematical differentiations, amount of change in time, during time. So now you can connect this to robot. Robot can understand changes in time, and based on changes in time can learn something. We will formulate this and you will see how to do that. And it is aiming to derive a prediction from a set of known variables. If we talk about the weather prediction, so based on the series of information that you have, you can predict future, right? So we have the same idea, similar idea in temporal differences learning that many algorithms are relying on this. What is the optimal control? It is a branch of mathematical optimization that we want to optimize the control that we have in the system. So it describes the designing a controller to minimize or maximize the measure of the dynamics of the system behavior over time. That if you are familiar with minimization and maximization problem, like if we show it in 2D environment, we want to reach this target point. This is maximization. If we want to minimize, we need to go there if we have two variables. So what does it mean? It means that let's imagine this is solution space. Like each point is a solution for a problem, whatever problem is. So best solution, if its maximization, is over here. We want to find best x and y to reach this point. That's just simply a maximization problem in optimization. If you wanna minimize the problem, what is the example? Like you wanna drive your car from Taipei to other city, and you wanna use minimum amount of gas. That's minimization problem in optimization. What is the solution? Where is the solution? We want to find best parameters. If we have two parameters, x and y, to reach this way. And the problem for us is to find the x and y. That's the optimal control. And of course, this is applicable in machine learning, reinforcement learning, artificial intelligence, optimization branches, and whatever you are coming outside of the for loop coding. That I also try to explain it more. So how this is happening? We usually have an objective function for chosen actions. That this objective function tries to help us to do that. What is the objective function? Who knows? So anybody passed here neural network course or deep learning? Machine learning? What you studied then? Last semester? Okay, mostly you are new then. So anyway, I will try to clarify everything for you from zero. Don't think it is hard. I'm explaining everything that is important. Okay? Just pay attention to learn the things, connect them together. If you can connect them together, you will see how sweet and how interesting it is. So objective function says, okay, you want to solve a problem. In that problem, you need to evaluate the current state of the environment. You want to say if I'm here is good, or if I'm there is good, or if I'm there is good. That's the objective function that I need to write some equation that if I want to go to that corner of the class, of course going that word is better, right, than going there. So I need to write some simple equation that shows me if I go that direction is better than this direction. That's called objective function. Clear? Okay, I assume clear. So what we can do, for example, we write Euclidean distance, the distance between 2 points that you studied in math. So if we have point x1, y1 somewhere in 2D coordinate system, and we have another point x2, y2, if it's two-dimensional, what is the distance between? Is Euclidean distance. You can write this term. This gives you the distance, d equal to this one. So this can be our objective function. For example, in simple example, I am here. My function, objective function, if it's that corner and the coordinate is 0, 0, or whatever it is, I can say, okay, xt target This can be 1. And the y target, and this can be 1. Then my distances from the target point and current, if this is robot current distance. And every time this gives you a d online. If your robot is moving, the xy is changing, and this is the target point, and each time gives you a distance. And you getting closer, then you can say, okay, d is smaller, better. I want to minimize d to 0. Because 0 is mean that I went there. Right? This is objective function. That's very important to define here. And we call it here reward function in reinforcement learning. We will define it as reward function, that some equations or definition that shows us how good our state of the agent is. Any question? Okay. What is the dynamic programming? If you never heard about it, you may think that's complex, but it is not actually. The method was developed by Richard Bellman in 1950s. This guy, Bellman, is an important person for us in this course. You will see later. He's very famous. And it is to solving complex problems by first breaking down them into small sub-problems, then solve some problems first, then use the same thing, same results to solve big problems. So simply we call it as dynamic programming. Solve a complex problem by first breaking down, then solving its sub-problem, then storing their solution to avoid repetitive computations. But there is an important point that I see students mix them, and that is mixing it with recursive algorithms. It is similar to recursive algorithms, but that's different. I hope you know at least what's the recursive algorithm. That's basically programming. So you write a function. For example, definition, action. Then you write something, then you call action. Call itself. So this is, of course, the simplest starting point of the programming, and you can call itself to solve something, and in middle somewhere return out, so that in recursive way the calculations will finish and you have the result. But here is a little bit different, similar but different, because the difference is here we want to break the problem, solve sub-problems, and later merge them together and store the solutions in forms of tables. How? Like this. We have famous Fibonacci problem, simple math problem, the problem that you learn at the first point of when you want to learn programming. For example, what is the problem? Fibonacci, we have two numbers, a series in math that starts from 0, 1 and continues with sum of the two latest ones. Sum of the 0, 1, then the third number is 2. Sum of the latest two, 2 and 1, is 3. Sum of the two latest one, 2 and 1, 3, and sum of the latest one, 2 and 3, 4. So 0, 1, 2, 2 and 1, 3, 3, and this should have been fine. Okay, then this continues. But how we can code it in form of dynamic programming, if you did it already, we can solve this problem in recursive way, but let's see how we can do it with dynamic programming. Here we have Python code, that in Python code, also I can explain it a little bit. We have definition of the function name and the input argument, then colon. So you can define a function. What is the function? Function is block of code that you can call it from somewhere else in your program. Write a block, whenever you need it, you call it. So when you call it, you can send some values to the function that you have. This is input argument. That n is a number or value that you can send it to there. And you have access to the variable n inside your code here. Then what we do here, we created a list, Fibonacci, n added by 1 times of none. It means that I have a list that inside it there are n times plus 1, 9. None. None is mean nothing. Then I can initialize the first start of the value, initial values of the Fibonacci, like Fibonacci 0, Fibonacci 1 equal to 0 and 1. In Python, you can write in this form. Like you can allocate the numbers directly in one line. 0 and 1 goes to 0 and 1, and it's starting of the sequence. Then we have a simple loop. That in simple loop, what we do calculation of the sum of the two latest one. So how we define in for loop in Python, if you're not familiar, of course you must study quickly. For I in range 2 to n1, n added by 1, it means that we are creating a loop, a repetitive structure that from I, what is the number, what was this? For example, if it's 0, 0, whatever it is, up to range of, sorry, I want to correct this, that's in C. So here for I in range of, so it means that in range of 2 to n added by 1, in this range, whatever the value is, it can be 100, 2 to 101. Each time I will be representing one of the elements of this loop, so that Fibonacci I is equal to calculation of the two previous ones, I minus 1 and I minus 2. It means that since we are beginning from 2, at the beginning it refers to number 0 and 1, and sum them up, and the result is as 2. And we do it in the for loop and return the Fibonacci. And returns the value for function, and you can print the result and Fibonacci 6. If you send 6, then this 6 comes here, it calculates and returns what is the result to the to print it out in the code. So with looking at this example, we can understand the dynamic programming that tries to store, like break the problem to small parts, how it does, like instead of calculating whole problem together, breaks it down, calculating 2, 2, 2, 2. Then finally the result will be the output that we have. You can use it as result. Print all the sequence, or print the latest one up to result that you want to print, or get average or sum or whatever you want to do. So why I'm explaining very basics of this, because you're gonna program, you're gonna develop some codes in reinforcement learning, and if you are studying and I'm explaining many things, basically we are going to move toward dynamic programming, and we will see 3 different algorithms of dynamic programming, how to solve our problems of reinforcement learning. Because of that, we start from here, just brief introduction of what is happening. Any question there? Is everything clear? Good. Try that code in Python if you're not familiar. If you're a good programmer, you may are laughing now in your mind, but that's fine. So now we want to talk about the general perspective of where we are. We want to see machine learning. What is the machine learning that all the time you're hearing, studying on the internet from your friends, or from your professor? So machine learning is a type of artificial intelligence that allows us to predict outcome without being explicitly programming something. So how it is possible that you don't write exactly code for a robot what to do, but robot knows what to do? You want to detect something in the picture. You have frames of picture, you have webcam that connected to your computer, you want to detect something there, and you don't know what it is even, and where it is, what color it is, it detects for you. You just say, I want to find something wrong, and it detects for you. How this is happening? With machine learning. And machine learning, without explicitly programming, can learn to do this. So, as I explained, we have learning with sampling data. You show the machine learning algorithm some samples. For example, you say, this is a marker. You show different kinds of marker to machine learning algorithm that you have, pictures, and machine learning knows, oh, this is marker, okay, I know. Next time in the picture finds it for you. How? We have, again, hundreds of algorithms. Which one is famous for this application? YOLO. You look at one of the deep learning algorithms that is famous to detecting that and can detect 100 different objects in one frame on 30 to 60 FPS in normal computer, frame per second in normal computer. And that's very strong, thanks to machine learning. So we have the artificial intelligence, lot of algorithms here. I briefly introduced different search techniques in this data space. For example, we have A-star algorithm and many algorithms. Then inside AI, machine learning is part of AI that is trying to cover this part specifically. Then inside machine learning, we have three different classes. One is supervised learning. That's very famous class, supervised learning. What does it mean, supervised learning? It means that we have labeled data and we have prediction, the future from outcome. So what does it mean, labeled data? Who knows? No idea? That's very strange for me. Labeled data in machine learning algorithms. Yeah?
Maybe if I have a picture and it's labeled with what is in this picture to train my algorithm to say, yeah, that's a horse. And then we look at the outcome, yes, horse, no horse.
Exactly. Correct. You have lots of pictures. You have dog, cat, animal inside. You say, this is the dog. This is the cat. You label it. You didn't do that when you're registering in websites. Asks where is the pedestrian, where is the airplane. Shows the picture that it is. You are labeling for other people. And there are big companies that pay people. They sit there and do this labeling. They need to sit, and there are pictures. Where is the dog? They mark the dog. Next time, where is the cat? They mark the cat. And they were paid. So, and you are doing that in computer. I'm sure you did it at least once. So that's labeling. And if your algorithm is using labeled data, it is very important, so that we know where is the cat. We know what is the cat, and we know the output. That's called supervised learning. Huge, like tremendous branch of machine learning is here. Then second one is unsupervised learning. In unsupervised learning, we say, okay, let's say we don't have labeled data. If you don't have labeled data and you want to find the hidden structure of the data, then you have unsupervised learning that is harder than obvious from supervised learning, because it needs to find the hidden structure of the data, and we have also lots of algorithms here. One of the famous and simple one is k-means clustering. What is the k-means clustering? Let's say I have this graph and some data, x, y. So each one of the points can represent something. You can consider x is size of, for example, home. You want to buy home. This is the size, and this is the price. Size is bigger, price is more. You need to pay more. Okay, clear? This is, each one of these are representing one home. Size of the home and price. Okay, this is your data. For example, in algorithms like k-means, what we are going to do, we want to have a machine learning algorithm that can divide these to different classes for us. So if I tell you to divide this to 2 classes, what you do, how you split them, you must probably say, okay, this is the one class, this is the one. Right? This is the most reasonable division that I can do as human, as intelligent person. Right? The same procedure we have with machine learning. But in supervised learning, we basically say we have 2 classes, find it. In unsupervised classes also, we can say, okay, we don't know. This is the data, what you want to do. Machine learning says, okay, looks like 2 classes, 3 classes. Let me divide it. Is it possible? Of course it is. This is like the most basic of the machine learning technique. Of course, we are not going to talk about those. We want to see where we are and what we are going to do. So, is it complex? No, this is very easy algorithm. You can learn it, just Google on the internet, and quickly you can implement it. That's k-means clustering. But now, what we want to do, we want to say, okay, we don't have supervised learning, we don't have label for our agent. And we don't have unsupervised learning kinda too, because it is not like labeling. We have a little bit different problem. We have agent that is doing something, not like working with pictures, detecting the classes like that. We are not solving such a problem. We want to have agents that do something in the environment. To be able to do that, we have third class of the machine learning that is called reinforcement learning. Reinforcement learning learns the interaction model of the environment. It means do something in the environment, do the stupid thing, good thing, bad thing, then tries to learn the outcome. And of course, it relies on reward and decision processes. Any question? So we are going to dive in here. We have one more step, and what it is, reinforcement learning can be boosted with some newer techniques that is called deep learning. And this deep learning is over here. Deep learning helps us to understand much more complex environments. If our environment is very, very, very complex, then we have new technique called deep learning that can be merged on the reinforcement learning. Then we call it deep reinforcement learning. Then it can solve much more complex problems. But of course, deep learning is not limited to reinforcement learning. It is also for supervised learning and unsupervised learning also. So I already explained what it is, supervised learning, training set of labeled data for supervised, for unsupervised, finding the structure of hidden data. But reinforcement learning is trying to maximize reward signal through interaction in the environment, although the structure of the environment is hidden sometimes for the agent. What does it mean it is hidden? It's like if I'm robot, not human. And if I hit this guy, what happens? I'm robot, I don't know. I should hit and see what's happening. If I hit the table, what happens? If I fall down, what happens? If I touch electricity, what happens? So the structure is hidden. I know if I touch the electricity, I die. But robot doesn't know. So we are going to not to tell the robot if you die the electricity, you're going to die. We are not telling the robot how to flip this and catch it. Robot needs to learn. Agent needs to learn. That's the beauty of reinforcement learning. We're not going to tell anything. We can tell. We were telling all the time before reinforcement learning how to do this. You can write some code to do this motion with your robot. You can write some code to do that. But in reinforcement learning, the beauty is that we don't want to tell what to do. So here we have another figure that is also decent, nice, and because shows some applications in machine learning, shows some more algorithms in machine learning for supervised algorithms. We have like two kinds of classification and regression problems. You may hear these regression problems. We have a couple of different examples, like market forecasting, estimating life expectancy, population growth prediction, or all the predictions can come to the regression part. That regression goes toward mostly math part and the estimation of the future. On the other hand, we have the classification. That classification is like we have image classification, identity, fraud detection, customer recognition, and the diagnostics. This is a part of applications for supervised learning. For unsupervised learning, we have dimensionality reduction or clustering. So these two are same, classification, clustering, trying to split the data. But here, in supervised learning, we're gonna tell how many classes we have. Here we don't wanna say, because it finds the hidden structure. So if you keep this in your mind, this is very important in your life, even in computer science. What is the differences of unsupervised and supervised? Just remember this clustering and classification and that figure. And that clarifies everything for you for every algorithm, thousands of algorithms that we have. And here also some applications, but anyway, reinforcement learning, that is like real-time decisions, game artificial intelligence, robot navigation, learning tasks, skill acquisition, and many others that can be in this class. So that we say, therefore, we consider the reinforcement learning as third big class of the machine learning that we are talking about. So there is no expert in supervision during training for reinforcement learning. It means that I'm not going to say to my agent that in middle of the job I see that doing stupid things. I'm not going to say you're doing stupid things. At the beginning, I'm going to write reward function, that what is the general good thing, like Euclidean distance I wrote for you. But I'm not going to say anything anymore. You're going to die or learn. It's cruel, but that's how it works. Environment is usually a stochastic. What was the stochastic? You see, last week we talked about it. Random. So if you don't know a stochastic, we are going to solve a stochastic problems. And we have class of stochastic problems. And you go search on the internet, Google book, you read about if the problem is stochastic. Then you're going to get confused. You must understand the basic things that we have in the class. So when the environment is stochastic, it means it's random. I exemplified for you. Randomness also is not only something is moving there here in this course. It means that I'm going to move to the right. I want to move to the right from there to here. But maybe it won't happen. I'm thinking I'm going there, but it is not happening in real. The actions that you are running, you're trying to, this is the object, your robot is trying to grasp it. Object is there and robot is here, and you're sure that you moved, you did everything correct, but there are some probability that it didn't work. Because of that, we have a stochastic problem. Because of that, we have lots of equations to formulate this. You will see in next chapter, if I'm not wrong. We will formulate this stochasticness with transition probability that we will see. The model of the environment can be incomplete. It means that we can have model, we can not have model, and we can have incomplete model of the environment. So also in Markov decision process, we will talk about it. Delayed feedback is possible. What does it mean? It means that you eat sweetie, that's delicious. Quickly you get feedback. But sometimes you eat some vitamin. Do you feel something at that moment? No. But long term, that's beneficial for your body. That's called delayed feedback. Is it important? It is very important. Because your agent is not only like, if your agent is going to get happy quickly from very instant results, then it's like kid. You know, you give the candy to the kid, he or she is very happy. Nothing important anymore. But when you get adult, you may think, okay, this candy is not good for my health, or money is better, or I don't know, if I don't spend money for candy, I buy home is better. So those are the things that come to the delayed feedback that is important to be considered. So if you want to have an application domain, general perspective of application domains, we have computer science, engineering, mathematics, economics, neuroscience, physiology that you can use reinforcement learning. So when I always talking about robots as example, it doesn't limit to robots. There are very nice applications in each one of these fields. So you can see that we have reinforcement learning that is connected to different sciences, machine learning, reward system, classical operant conditions, bounded relations, and etc. That all goes to different sciences that I listed there: engineering, computer science, mathematics, economics, neuroscience, and physiology. So up to now, it's very clear for you. We have the agent, wants to do some action. We have the environment, and this action can be good or bad. And how we can detect it based on the state and the result that we are getting back as feedback. Feedback, what is it? The feedbacks are sensors. Sensors, depending on what we have, can be read and understood by the agent. So here, let's say this robot is looking for apple tree. Think about it. How reinforcement learning or how our agent can find apple tree. So tell me what's the solution that comes to your mind. Like if you are a robot, what you do as one agent. So imagine you are there instead of robot and you are agent. I told you human can be one agent, right? So what you do? And the question is find apple tree. Oops. Here.
Look around, locate the tree, look what's the angle to my current facing to the apple tree, turn that angle and walk straight.
Yeah, that's one strategy. Very nice. And each one of you must answer for these simple questions. Okay? So simply look around. I want to find apple tree. Look around. Look around means try and error. And look around means reinforcement learning, try error algorithms. We want to formulate that. You see how beautiful it is? How we are thinking. Other researchers already thought about it and formalized it. We will see in this course. And finally, we will achieve decent results. So there are also some points I can discuss here. For example, finding apple tree, what can be the reward? Or like let's break it down. Looking around, what does it mean looking around? Looking around means moving randomly around or moving by purpose around. Moving randomly around is a solution, but is it good? Maybe let's say here in this part there is no tree and there are plenty of trees there and robot moves this part. That's not very wise. It's maybe better to go toward where there are plenty of apple trees to find them. Because maybe they are far. Maybe this is not apple tree. They are far. Robot cannot detect from here. Should look around, move a little bit closer to see where the apple tree is. So we also see how we can do that. What can be the reward here? Think about reward now. If you are agent and you want to move, look around and find apple tree, and let's say apple tree is over here and we don't know where it is and we cannot see it from here. Our vision is limited. We just can see few meters around. We cannot detect so far. What you do?
Measure the distance between the robot and the trees. If the distance is more closer, then give it a reward.
Yeah.
Point.
Yeah, very nice answer. We can say, okay, if we are closer to the trees, whatever tree is it apple tree or no, that's good for us. Go to our trees to find apple tree. And if it's apple tree, da-da-da-da, big reward. We can say, okay, big price for you. You should be happy. Yeah?
So in this case, you don't have a reward for any iteration, or you just have a reward whenever you find a solution?
So we can have different types of rewards. For example, you can say, okay, if each tree that you are close to get reward of 1, but if it's apple tree, 100. Then if the robot gets close to trees that there are 10, you can get rewards of 10 with robot.
Sorry?
If your robot is getting close to trees that there are 10 robots, then your robot can get reward of 10. But if there is apple tree, it can get reward of 100. And this happens inside the loop for a long time.
So the way I'm picturing is, suppose I can choose like 10 iterations, right? So in this thing, because I can set up the number of iterations.
Mm-hmm.
So suppose I choose 10, and in those 10 iterations, it gets closer, but it doesn't find the apple. So then it gets like a negative reward.
Yeah, you can do again. You can do again, but don't mix them. Kind of reward is not related to iteration. Reward is kind of say, okay, if you find the answer or not.
Yeah, no, I get it.
Yeah.
How you frame the reward is like a distance measure?
Can be.
It's like if it's above this distance value, it's positive, and below it's negative.
Yeah, up to you.
Okay.
Yeah, as designer, I can design it. I can say, and this is also very nice question because you need to, in many applications, change your reward system. You see, this reward system is not working. I'm telling my agent, if there are, you find the apple tree, you find the trees, go toward it, right? And my agent, let's say I'm saying if there are, for example, 10 apple trees, that is better than 1 apple tree. In far, we don't know is it apple or not. And your robot tries to go to see those 10 apple trees. But let's say there is no apple. Those are just 3. And the apple tree is the one that is over there. It was better to go there. And always your robot is learning to come to collect this 10 reward instead of going to looking that one. And this is the reward system. Me as designer should choose it wisely, somehow to find the solution that I want.
So and then stochastic will mean like taking steps of different lengths at each iteration. So
No.
for example, I'm step 0.
Mm-hmm.
Okay, so I'm position 0,
Mm-hmm.
and there is a tree out there somewhere.
Mm-hmm.
So I can take one step of 10 meters, or I can take any step. So stochastic means randomly choosing the length of the step.
No, no. Here, stochastic refers to the unpredictability of the environment. It means that you want to do some motion, maybe it's not happening. You want to move one step, but you move half a step. The stochastic in the environment here is mean that. That one that you're saying, you're choosing different actions, that's random action choose.
No,
that is mean.
actions, different length of each action.
And that's this discretization of the environment. If you mean the length, we say this environment.
Yeah, exactly. So that is not stochastic. Right?
No, no, no.
So stochastic will be I can move anywhere, so that's not stochastic. This is the freedom of the action space.
Yeah,
So that space could be right, left, forward, back.
that's discrete. Yeah.
Okay, but then for each action that I take, I can stochastic. What I think it is for example I can do left, but I can do left 10 meters or 20 meters.
No, no. That's amount of discretization that you decide again. You decide that how stochastic my environment should be. So we have two kinds of environment, continuous and discrete. So last week I a little bit explained. In continuous environment, the action space is continuous. But in discrete, we have discrete that the step size can be defined by you. But stochastic means that, like, if let's say this is the environment that we have, each one of tails that you can see is discretized for my environment, and each one is one step. Instead of considering small steps of me that can be, I say I can be here and I have 4 options, up, down, left, right. This is discretized, and the size can be vary based on me. I can make bigger tiles, make smaller tiles. I can consider whole room one state, next room second state. This is discretization of the model, the environment that I have. But stochastic says, okay, from tail A, I want to go to tail B, but maybe I don't go. What is the probability of don't go or go?
Oh, there's a probability of like squaring.
Exactly. Exactly. And that's called transition probability, that today I will also formalize it. And later we're going to use it as key element of our algorithms. Any other question?
This map of probabilities is like randomly chosen.
Yeah. Not completely randomly, but if we have also 2 branch there. If we know the probabilities, that's one branch of algorithm that we know, transition probability. What is the chance that if I want to go from here to there is running? 99% or 50-50? Of course, if it's 50-50, I don't know that. That's kind of, I don't know. But if I know, that's helpful for me, and we will formulate it and use it in our solutions. But if we don't know, then we say, okay, we don't know the model of the environment, what to do then? Everything is 50-50. And we have algorithms that we will dive in soon. Soon, I mean after finishing those. Okay. So if you want to have a definition, another definition, reinforcement learning explicitly considers the whole problem as goal-directed agent interacting with the uncertain environment. What your friend asked. In solving different examples, we can involve explicit goals also that agent can judge the process. So when it is explicit, of course, exactly we know. But you can now ask, what about if the goal is implicit? Is it, can be, or no? Okay, you guys, I think sometimes is sleeping. So this is homework. Then I don't answer it. Can we have reinforcement learning techniques for implicit goals? This is your assignment for next week. Answer it. If we do, how and what?
Where can I find your, because I can see people are looking at your slides.
Huh?
You have your slides available online?
Yeah, I share it in Moodle. Do you have Moodle? If you have Moodle, I share it in Moodle. You have the email, you get email and you can open the slides there. And soon students are recording the classes also, they will be available, I guess, so that you can watch it. And I will send you the instruction how you need to, the deadline and how you need to send the homeworks and assignments.
What is the question again?
What if we have implicit goals for reinforcement learning? What happens? How we can solve it? How we need to, no need to answer exactly how to solve it, how we need to consider implicit goals if we do have.
How to consider explicit?
Implicit. This is explicit. We can have explicit, exactly the goal is there. If we have implicit.
Like how to approach the algorithm?
How to define it, how to consider it.
How to frame the problem in reinforcement learning for implicit algorithm?
Exactly. Okay, so for students who are new from undergraduate, this is graduate class, of course you should be more interactive, more research-based, try to study, try to learn. And if you come from the beginning things that I'm explaining to you, you can become very good experts soon. Because there is nothing that I'm not explaining almost, right? And if you don't catch, that's your fault, I'm telling you now. Because I'm explaining everything, every connections, whatever the details are, how this is working, how that is working. If quickly I go to advanced level and you don't understand that, you must go learn, usually in classes, but since I'm coming from scratch, please try to catch it, every detail that we have in class. So, because this is the reason that you can, I told you, it can be, whatever you're doing here can be your final project for master, for PhD, and this can be applicable in your work. Now, some of you guys know, we have some of friends that are working in reinforcement learning in Taiwan with some companies, and they are developing reinforcement learning algorithms for those R&D of those companies, and they are also well paid. Whatever you want to do, this is very useful. And if you want to go continue your PhD, apply for some position, especially for abroad, United States or somewhere, you will see many of professors ask for reinforcement learning because it's important. So we say the agent can use the experience to improve performance of itself during time. What does it mean? It means that, okay, of course, we need to have some structure that agent has experience. With trying something, memorize some information that information can be useful later to make decisions. Of course, this is obvious. How we can do that? We exactly, precisely formalize it. How we can have experience for our agent, so that based on that experience, that can be, for example, simply table, that based on table, the agent can look at that table and understand, okay, I'm going to do, in this condition, better to do this. Make decisions. Then, for instance, also we have chess player that defines the intuition of the evaluation of the position during time. Every time he plays chess or she plays chess, based on the similar situation that he is or she is, may learn something and refine the strategy. So that defining the strategy means that updating the experience. How we can update this experience? Exactly, we will formalize it in this course. Precisely, we say, okay, what is the equation to update the experience based on the state that I am in the whole state space? Very clear. And you're gonna write some code. I will show some examples code that solve problem with this using the experience. So we also say reinforcement learning refers actions that has tried in the past and found better effective ones to get rewards. So of course, when agent do something in some state, maybe there is another one better one that we will define the definition of the exploration exploitation in the next chapter, and we will dive it into details how agent can find better options to move to one. So basically we can say, we can conclude ourselves that agent needs to try a variety of actions to see which one favors the robot or agent much more. Reinforcement learning usually uses the formal framework of the Markov decision process, MVP. I will exactly clarify what it is from basics, that it helps to define the interaction between learning agent and the environment. Because if I'm agent and I'm gonna try everything physically, is it possible? That's a little bit hard. It's better to try to construct model of the environment. Kind of let's try to guess the model of the environment at least. What will happen if I hit that guy? And if I hit that guy, something happens. Most probably if I hit that guy, same thing similar happens. If I say good word to him, if I say you're handsome, you're good boy, and you're good student, he's happy. Now he's smiling, I see. And that guy is also will do the same. And this is the agent that we can generalize to learn the things from environment, the general rules of the environment. Of course, there are some exceptions. If you say something good about some person, maybe he gets angry. That's very exception. So in Markov decision process, we will see how we can model state action and rewards. And of course, based on these things, as I mentioned, we have exploration exploitation topic that we have very nice examples to understand these in next chapter. So I will give you 2-3 minutes, 5 minutes break. 3 minutes you can rest a little bit, then we talk about the examples and go more in details. So we have AlphaGo and AlphaGo 0 that are reinforcement learning based algorithms, that they are for playing the game Go. And if you are familiar with the game Go, there is a board that you should put some stones to occupy much more space and enclose much more space there. The thing that has happened in March 2016, reinforcement learning beat the world champion Lee Sedol in 5 games match. That was very interesting and attractive point that there were lots of news. I highly recommend watch the video. This is 1 hour around documentary of what's happening, the emotions of the Leo, that he's like he played the game for whole his life and he's the best in the world and no one can beat him, and computer for first time beats human in a complex game like that. And that's very interesting, and I highly recommend to watch the video. And one of the points that is happening in the middle, there is some move that in that specific move everybody thinks that the computer did mistake, or the expert players that that was the mistake, he's gonna win. But after a while, they see that no, there is no mistake from computer and reinforcement learning. And that was brilliant move, because nobody ever think about that move that is possible and that's good for future. No human think about that, but reinforcement learning found it in somewhere in middle. And if you watch the documentary, you will see that those moments, and you see that his face, he's like very proud, and he's like, oh, okay, I'm gonna go win. I promise you people, I'm gonna defend you. Computer cannot beat us. And at the end, he's like, oh, I'm sorry. I couldn't do better. So that's how reinforcement learning can be helpful for us. It's mine. What happened to this guy? Okay, now it's working. Now if you want to just a little bit understand what's happening for each example that I'm saying, so we need to answer some questions, because of course you're going to face with many problems. That those problems you need to first answer what's the environment. The environment here is the board and player. The most important part for us is the board. What is the agent? The player itself. What is the state? The board configuration of the current state. One state is the current board configuration of the game. What is the action? For example, placing a stone on the game. So you put somewhere. So how many actions you can do? You have one kind of stone, and how many possibility points that you can point, that's your action space that you can put the stone on the board. What is the reward here? Think about it a little bit now. Whatever the rule of the game is, you finally want to win the game. Final reward is winning, but current reward can be evaluation of the current situation. So how can I evaluate current situation? So I can put some simple equation to sum up all the situations, sum up all the rewards that I'm getting from the game, for example. So it can be the winning or losing position and or current evaluation. That also soon we will see there are critical differences between these two. Another example, the data center cooling. Data centers are kind of servers that are working in background to do computations for you guys, like Google have lots of those data centers to store data or do some computations for you. And one of the world's most challenging physical problem is energy consumption of these data centers. And data centers are kind of, because always they are keep running, you can kind of manage them to improve the energy consumption. That's very important. As important as that, they also doing costly operation of bringing them to the inside the ocean to cool them down, to use less energy instead of using big systems to cooling down. That's very important. So because of that, Google data centers are using machine learning algorithms, reinforcement learning algorithms to reduce the amount of energy, and they achieve 40% of saving energy. And that's tremendous big money. That if you are Google and you're saving 40% of the bill of electricity, of course I think 40% is also important for you guys if you rented a home and you're paying for your bill for electricity. And they did it with the DeepMind, that this is another application. We have the environment here, that all data centers are environment. You can consider data center kind of as big computers that they can do computations and store data somehow. What is the agent? Data center controller that wants to control the data centers, which one to work, which one not to work, which one get off, which one get on, based on the load, requests. All these are important, and that can lead us to say 40% that I mentioned. States is the current estimation of the energy usage at time t. Actions, moving the load, turning on, turning off, I explained. And reward is if you use less energy, your agent gets reward, simply. Another example of reinforcement learning is trading and finance that you can see. We can have supervised learnings and reinforcement learnings for predicting the feature of the sales of the actually supervised learning can predict the feature of the sales, but they cannot do action. That reinforcement learning can do action also. It means that you can use reinforcement learning to say to hold, buy, or sell. That finally you can get profit. Is it working? Yeah, it is working. Do they give you profit? Yeah, they're selling their apps. They are advertising a lot. You may have seen that. So should we trust them? Up to you. You can develop your own code reinforcement learning. That's more reliable to try, of course. But the point is that you should train it. So if you train it and it works well in like last 10 years data, then it should work in future too, so that you can use it for your own self or sell it even with reinforcement learning. So reinforcement learning make decisions whether hold the share, buy it, or sell it, and when to do that. For example, IBM has a sophisticated reinforcement learning based platform with financial tradability that, you know, IBM is very famous and they are doing very well. What is it happening in background? We have data analyzers, we have reinforcement learning agent that is training based on this analysis. Then it goes to simulation and paper testing, and finally it adopts into live trading. Then really you say, okay, this is my bank account, this is my money that I have, buy and sell share automatically. You don't know. The reinforcement learning goes and buys unknown share from unknown company from somewhere that even you cannot imagine if you don't know which country it is. It is buying and selling and finally making profit for you. You would say for like just Google, Amazon, famous ones, but reinforcement learning learns how to do that to get more profit and works even pretty fine to do that. You may say, okay, if you have that one, we can become very rich. Yeah, you can, if really it works. And if you have access to that, of course you can become rich. And they are using it, of course. IBM uses it, such search about it. And search about big companies, do they use it? Some of them, yeah, they are using. Why they are not risking everything or always using that? Because of course it's not 100%, it's maybe 90% working, but that 10 times, of course you need to be still careful. Something unexpected happens, war happens, I don't know, earthquake happens, something big happens, then you lose all money. Because of that, they don't investigate all money on such techniques. And of course, there are many steps to improve still that I'm sure in future 10 years it will be, because of new hardware that released recently from NVIDIA. Later I will explain to you. From NVIDIA, there are new even CPUs, new graphic cards that you can connect directly to the internet. There is no bottleneck of CPU and GPU anymore. They are creating a new revolution of the hardware in order to solve such a problems. That in future 10 years you will see that we will see a lot of progress over there. So what's the environment here? All the traders and the shares. Agent is the trader, that the guy that wants to buy or sell the share. It states the amount of the shares status. Action, sell, buy, hold, and reward is the profit. But I want to say you don't go invest your money on those apps, then you lose it and you say, our professor said they are working. I lost all my money. No, your decision. Of course, some of them are not good, some of them are good. That's also a little bit tricky. The safest one is that you develop your own. So we have healthcare, another application. We've seen in some example in artificial intelligence part. Healthcare has seen a significant tilt toward reinforcement learning, and because of the dynamic treatment regions or DTRs, the patients can be treated in long term, and this is also useful. But since it is a little bit risky and plays with people's life, still the progress is too slow there. Choosing medicines is hard because of that problem, so that you can see the kind of general structure what can happen here. The medicine that can go to the hard-coded or supervised learning or reinforcement learning techniques, that these techniques can help us to deal with different kinds of diseases on the human. That of course we need to also use some other records and other data and evaluation of the human to analyze if it's working or it is not working. But since it is risky, not that easy, you just lose money, you may lose lives, you may lose days of living of people. Usually now they are working on animals, but of course it's still we have lots of like gene sequences and changing them and simulating to see what's happening in human life. It still is applicable in that reinforcement learning. So environment is patients and all treatments. Agents are recommenders. States are patients' current health and status here. Action can be advising medicine, and reward can be the health improvement of a person. And one more application that we know better is robotics. In robotics, we can have many different ones, but one is the grasping object, for example. And if you have grasping object, then you can think how reinforcement learning can do that. We have hundreds of different papers on this topic. So you can see an example based on the sensor that it has. It can grasp it. Reinforcement learning as action says the joint positions, how to work in the state space to finally grasp the object. Environment, we say, okay, also reinforcement learning can be applicable in all kinds of robots. I already explained. Environment is the robot and workspace. Agent is the robot itself. State is the robot joint's position and object pose. Robot position and object pose, not only robot itself. Maybe I'm gonna grasp that object over there. Maybe it is there, or maybe it is somewhere else. That also is including as my environment state space. Actions are robot movements, and rewards. What can be the reward depending on what we're going to do? Here, grasping object, if the grasp was successful or not. Now you should think, okay, I'm gonna learn reinforcement learning, and there is a question of the reward. And here is the grasping is successful or not. How can I do that? How you can do that? You have robot, you know how to control it. Let's say you know reinforcement learning and you know how to solve it. But in one of the elements we have reward, and finally robot should know that if the object is grasped or not, successful or not each time. How you can do that? I grasped it. How you can say that I did it?
Optically or with the force your fingers into a flap?
Yeah, of course, you use your sensors. You use your camera vision, if it's here or not. I pick it if it's here or not. I sense it. So you need to implement the sense of the environment. You need to you need to implement the vision algorithms that say what is my reward. Depending on the problem that you have, you want to give feedback to your robot, and that's the reward that you need to implement that part, the success. And maybe sometimes it is also one of the challenges that you have. If your robot is flying, is drone, if the balance is 0, that's nice, right? You try to make 0 balance maybe when it's flying, or good balance, or good movement, exact calculation of the what. So your robot drone flying from here to there. Your objective is your robot learns how to fly from here to here. But how you can evaluate you are here or somewhere else? That's the reward that we need to also calculate it based on the sensor system that we have. That's also a challenge. That here I put question mark. These fancy applications should be considered how to find the reward. So repetitive but reinforcement learning, what to do and how to map each state to action. So each state, what to do, same thing. And the learner was not told which action to take. Instead, must discover which action leads to get higher reward. And so far, I think you clearly understand these. Actions may affect not only on the immediate reward, but also next situation and all subsequence of the rewards that you are going to get. Because, like, if I go out here, I never can get the reward to get to that point, because that's 5th floor, 3rd floor. I will be maybe injured hardly, then I cannot get to that point. So because of that, doing good actions can lead us to get final better action, better reward. So let's, now you should be able to understand all the basic concepts. We are going to talk it more formally. First, we divide the reinforcement learning into 4 elements. Then we start to formalize it. So we have a policy. We have a reward signal. We have a value function. And we have a model of the environment. So formally, we need to know this in order to be able to solve it. So let's first start with a policy. Reward, you know. Value, we should know. And model of the environment, I a little bit mentioned it as a Markov decision process, but I will explain. So what's a policy? We say, okay, the policy pi is the core of the reinforcement learning agent that determines the behavior of agent during time. What does it mean? Look at this environment. We have one environment that discretized to different tiles. This can be our class. Let's divide it to different discrete parts. And this is obstacle here. Robot cannot go there. And this is the target point. We want to go there. What can be policy here? What is your guess? The policy is mapping state of the environment to action. It means that, like, this is the policy that I can define for this environment. If you are in this state, go up. If you are here, go right. If you are here, go right. If you are here, go up. So the question is, why up here? We don't know. Can be random at the beginning, but reinforcement learning is trying to say, okay, what should be the policy here in this state in order to get to that target? What should be the policy here in order to get that target point? What about here? What about here? Of course, I solved it here already, up, right, right, and if you are here, up. And wherever agent is, if you want to go here, from each state, the agent can reach to the target. But in the reinforcement learning, we are going to say, okay, we don't know it, and our agent is trying to learn policy. Learn policy means that in each state, what to do. For example, here, four possible actions, up, down, left, right. Is it clear? Any question? So when we are talking about the policy, whenever, there are many terms. I'm going to use it a lot. So when I'm talking about policy, you should quickly think about the actions for each state that a robot or agent can pick to do. Clear? Okay. And of course, we have also some different small parts that different variations that I will show formalized. So in the same case, policy can be simple function or lookup table. So sometimes it is not like this table over here that you can say up, down, left, right. In some problems, you should have a simple function to show it. That simple function, later we will see. Or can be lookup table, a table that you can search in it. What is the lookup table? Is like one array, can be one simple two-dimensional array that are like 0, 0, and you can put some values here, 1, 2, 5, 2, 3, each one indicating one action, for example. So something happened there. Check what it is with that computer. Tony, please check that computer. Is everything fine? Okay, I think that's... Okay. So policy may involve existing computation, such as search process too. So sometimes we can have some search processes or small search techniques inside this lookup table that we have. In future, we will see how. Policies can be stochastic, specifying the probability of each action that is happening in the environment. As I told you, going to next state maybe happen or not happen, that is here in form of the policy. So this probability is important because kind of we are modeling the error of the environment also with this form that your agent is trying to do and it is not happening, kind of implicitly we are modeling the error. So second element is reward. We talked a lot about it, signal that defines the goal and defines it is good or bad, and the agent objective is to maximize the total reward of the environment. That's clear. But third element that is also important, for first time we are going to talk about it, is the value function. Value function says we have the value of state, that is total amount of reward that agent can expect in future from that state that we are. Kind of it is prediction the future from being at this state. So I'm gonna go here. Is it good or bad? I need to predict the future based on the evaluating the future to be able to say that state is better or that state is better for me by evaluating the next steps. And if you think about the chess game, value there, sometimes you playing chess and you can get some reward by playing each move means that like you're getting some pound. You you're hitting the opponent pawn, for example, or bishop in one move, and that's reward for you. But sometimes you need to sacrifice some of your pawns or your queen even to win the game finally. So you may hit your queen with something very like in some situation you may hit queen with like bishop, change your queen with bishop, so that in 10 moves or 15 moves finally can win the game. So it is long-term look and can gives you the opportunity to ignore sometimes small rewards. Sometimes saying, okay, if I'm getting punished here, that's good for my future. If I'm doing something, if I'm sitting here listening to my professor, that's very hard, that's brutal, but it is good for my future. Right? So that's the definition of the value. I think its battery is finishing. I need to change this one. So check if it's connected.
No, it didn't connect to the. It's not this one, right? It's different one. This is the.
So connected again.
But it's the. This one is battery is really low. I think you're not using this one, right? You change it now.
No, I changed it. Just disconnect and connect again. No, you don't need to add new one, I guess.
Maybe I just close it and reopen.
Just disconnect and connect again.
It's still saying it's battery.
Yeah, it's
on.
connected
Okay.
now. Should be fine now, I guess. Okay. So as I mentioned, value function is indicating long-term desirability of the our moves, and reward while reward signal also only indicates the immediate sense of the what's happening. So this is very important to be considered in reinforcement learning. Although reward is important, but long-term look is more important. I may lose something, I may buy something, invest on something and lose money, but in future finally I gain a lot of reward. So that's kind of similar to investment or kind of similar to sacrifices that you can have, that we have the value function. But also it is also defined as evaluating the next state by looking all the futures to how good it is. Same definition, well, how it is good in long term. So a state maybe always have a low immediate reward, but it still have high value. So yeah, this is nice. Pay attention. A state may always have a low immediate reward, but it still have high value. How it is possible? So I'm in this state, I move here. Reward is negative. I'm getting punished. But we may have very high value for that state. Why? Next state higher reward. Yeah, that's true. Because maybe I'm going here, I'm getting punished for some reason, but from here I can go here, that is the final target maybe, and I'm getting huge reward. Although the reward is negative here, but the value is very high for this state. That's the reason. So you need to imagine a little bit some examples, those scenarios, how that can happen. But this is very important now that you need to distinguish when we are talking about the value of this state and reward of this state. Who defines reward? We define reward as developer. Who defines value? Reinforcement learning agent. How to calculate it? We will see. We have equations to calculate. Depending on the algorithm, depending on what we are doing, the value will be calculated based on the rewards that we define. But that value can, of course, vary depending on the time and depending on the problem that we have. And what this value is indicating finally? The policy. What was the policy? How robot need to act at each state. So this is the backbone of what we are going to learn. Again, we define the reward ourselves for the problem. Then that reward results as some value per each state. And that state, that value per each state will tell us what should be the policy. What is the good policy? What was the policy? Was the actions that we wanted to do at each state. So these are connected together to solve the problem. How simple it is, we will see. How complex it is. This is the rule that you must know. So the answer is here. Maybe it follows by a higher rewarded state that causes that one for us. So let me show you one example. So this is close here, and I am agent. I am here, I'm here. And I want to go there to the end. Same example. And now, give me one more. And this part is also closed. I cannot go from there. I'm here, I want to go there. And I implemented my reward function as Euclidean function that I've written there. How much I'm getting close to that point, I get more reward. Right? Everything is clear, scenario? I'm here, my reward function is Euclidean distance, and I'm supposed to go toward that direction. It means that if I go here, I get reward a little bit, like 1 point. I go forward toward that point, I get more reward. But the problem is now, it is blocked here. If I come here, this is blocked, I cannot go there. And if I want to move right, I will get punished because I'm getting far. But I have to get punished. I have to get punished, for example, go from here to there. That is the explanation, very nice example of this one. So if you understand this, in very complex algorithms, in very complex problems, fancy problems, I will show you videos, you will see from NVIDIA and very complex simulations that exactly this is happening there. So that we can conclude without rewards, there could not be values, and the only purpose of the estimation value is to achieving more rewards. So for value function, better to choose the values that, better to choose the actions that we achieve higher values, not higher rewards, because of this example that I explained. If I want to get higher reward, I always try to go there, I stuck here, I cannot go anywhere. And this is also common to to happen in reinforcement learning. In simulation, you will see when you're solving problem. If your agent don't learn well, comes here and starts here, hits the wall, I'm gonna go, cannot go. And of course, it's obvious, it is harder. Reward is easier. You just can say, okay, this is the reward. But if you wanna know the value, you need to kind of estimate it. You need to kind of have some calculations, some estimation of the futures, estimation of the values of other states to say, okay, what I'm going to do. And this is called the hard part of the value, that we need to run whole episode mostly in order to be able to update the values of each state. So you see, I'm started already using the words. So the sentence that I'm saying, including 4 or 5 things that I explained to you. And next week, all the time is going to be happen like that. If you don't understand the sentence, it means that you didn't study. For next week, of course, study. What is the value? When I'm saying value of the state, what does it mean? You should quickly start. Value of the state comes from reward. And so there are many terms like this. Please, what is the episode? I'm not explaining anymore. Episode is like one round of starting from start point and go to the end. And end is not necessary there, maybe somewhere else. Might try, maximum steps that I define for my problem. For example, I say 100 steps I can go in one of my episode. That's called episode. My agent starts from some state and ends somewhere. That is not necessarily the end that I want. Maybe I'm wrong going somewhere else, but my episode ends. And I reset my environment to the, again, first starting point. Then second episode, third episode, I try like this. This is called episode. Last week we talked about. And when I'm telling about the value of the state in episode, now you should understand. That's a must. There is no way, if you don't understand reinforcement learning. Then let's have a visual example here. We have this state, and from this state I can run one episode. And this episode can have many steps that finally reaches the end of the episode. We call it as usually G. S, state, finally goes to the G. And what we are running? We're running the policy. We show it with pi. Wherever you see pi, you should understand we mean policy. What was the policy? What to do in one state. Is it clear? Then we can run multiple of these from single state. From here, I can try 100 times of running episode from whatever it is, randomly or something. And the value means that I can get, like for this state, kind of average of those, average of each time of running whole episode and getting the reward, and average of those can be my value pi for this state. Value pi for the S, value of the state for CH1. So this is called the estimation of the value for one state, and the simplest form is average. Are we limited to average? No. Then finally, we have model of the environment. In the model of the environment, we say we want to mimic the behavior of the environment. That reinforcement learning agent can kind of have the idea of what is going to happen in real environment. So we have a separate chapter to talk about this, and we will talk about the Markov decision process as one element of reinforcement learning. By giving the state and action, you give the state and action, the model predicts what will be resulting in next. So you say my action is moving to the left. Then model says most probably you'll be here. Simple. And model used for planning, which considers possible features of situations before they actually experienced. So you may think, okay, so we have agent. If we have simulation, we can run it. What is the purpose of having model? Model says, okay, when you are going to calculate the value for this state, so what we said, you need to run whole episode. And if you want to run whole episode to understand and multiple of those and finally get the value pi here, the policy of the value for policy of this state, then what you need to model that understands that and kind of simulates it for us, kind of shows the dynamicity that can be helpful to get the value. That's the main reason that we have the model of the environment. So if our reinforcement learning algorithm uses the model, we have model-based methods. If it's not using, it is model-free methods. So we have two techniques, one model-based, one model-free. Which one is good? We cannot tell exactly, depending on the problem. Sometimes that is good, sometimes this is good. And depends if we can model the environment or not. If we can do that useful, we can solve the problem better. If we cannot, that's harder, and we cannot certainly say which one is better. But we will study both in this course. So if we have model free, usually we refer it as trial and error learner, that we will see. Model reinforcement learning is also span both of them together, try to combine them in low level trial and error, and higher level try to generate models of the environment. How does it look like? It looks like small things I try, everything, but big things I say, okay, let's say from going to room to A to B, I can model, that's simple, but the small things are hard to model. The small things don't model, big things we can have model, then combine them together to have a much more modern technique. Okay, I think that's enough for today. I was hoping we can finish it. Next week we will first formalize the problem in mathematical form. So if you want to have a look, like we have the representation of how the equations look like, how we can do the calculations, then we continue with algorithms much more and dive in. Any question? So these are the things that we're gonna study next week. Any question up to here? Okay, so you have one assignment plus these topics. Make sure that all of you are confidently know what's happening so far, so that you understand the rest. And if you, as I told you at the beginning of the class, if you understand this chapter, later everything will be easier. Okay, thank you very much. See you next week. Today, basically, we are going to first have formal definition and kind of showing in mathematical form of the reinforcement learning. And as I mentioned, these elements are very important for you guys to know because all the time we are going to use these, and be careful to understand these basic concepts. So it's clear. We define this state and we show it usually with S. And current state, usually we show it with ST. So ST is the current state, and ST added by 1 is the next state that we usually represent on the state space. The action we represent it by A. And what is the reward? Reward can be represented in different forms. We show it as R or big R, S, and A. That this says, okay, the reward per the state S, if I do a specific action, what's the reward? So two different forms of representation in mathematical forms that we will use them. So me say actions may affect not only the immediate reward but also next situation and all subsequent rewards, because when our environment is continuous and your robot do something well, your robot becomes stable. For example, your robot is flying, by choosing good actions causes a stable situation of the robot, so that previous actions that we are doing also affecting on the reward, that you need to be careful when we are talking about the reward. What was the episode we discussed multiple times? I assume all you now exactly clearly know what it is. So robot or agent starts from initial point, do series of actions and end up somewhere. It can be limited by number of times that we specify, or we can say, okay, we achieved the goal target or we failed. Failure or success also can be termination of our episode for solving the problem. What is the transition probability? We haven't talked about this yet, but today also we want to specify that. Okay, we can declare the probability of reaching S prime with taking action at state t by the action that we have. So we can read it probability of S prime given by S and A. S prime is exactly same as ST added by 1, next state, that given by state and action. So if we define the values or the probabilities, not the value, actually don't mix it up when I'm calling value, because we have value function here and definition of the value, better to say the probability. If I define the probability of all actions possible from each state to reach to the next state, I have the transition probability that says, what is the probability? If I'm moving forward, our agent moves forward, will be at this current state. So from S, move to the next. I'm doing action move forward, for example. What is the probability of being there? As I clarified for you, so you may say, okay, if agent moves forward, of course it should be in next state and there. But actually, no. There are some chance that we run some action, but that action will not happen. And we can indicate it by probability. And that probability called transition probability. So the question is, do we know it? In some problems we do. In some problems we don't. In simple problems, we do. And if we do, we have series of algorithms. We will see how to solve the problem. Today, we also discuss it, if we reach it. But if we don't do, reinforcement learning is intending to learn it also. So we will have some examples to clarify more, numerical examples exactly, that you will see what's happening, how we can represent a transition probability, and how it is working. So per each one of the actions that we have, per each state, we will define the probability of the happening or not happening. If it's happened, for example, 90% it's happening, 0.9, 10% is not happening, 0.1 to be in another state or not happening. Any question here? This is very important because based on these, we have different approaches to solve the problems. And we have policy. We declared it. You know what's the policy now. And we show it as pi state and action, or pi state 2. It can be represented as pi state 2. So the policy, it means that policy by given state and action. What is the policy by given a state and action? So actually policy maps state, each state to action we declared, and it can be either deterministic and stochastic. If it's deterministic, we usually use it, as I mentioned, action equal to pi s. What does it mean? It means that in state S, what is the policy? This declares my action, right? And if we have a stochastic, we say, okay, that's for deterministic. If we say we have a stochastic environment and a stochastic scenario, policy indicates for action and state as probability of the AT being A given by ST given is equal to S. So among all the states, where the state is, among the all actions, what is the action that we run by given state will be in form of probability in terms that we have a stochastic environment. Okay, so maybe it's a little bit blur for you now. What we are going to do with this, we will soon see what's going on exactly with examples. But when I'm talking about policy pi or referring pi state action, you need to know what I'm talking about. When I'm talking about transition probability, you need to know what I'm talking about so that you understand the explanation of the course. Next thing that I'm going to define is the return. Return GT, we usually show it as GT, is the total future rewards at state ST. It means that my agent is somewhere in the environment, in the state space. GT indicates the future, all the next states that my agent can go and sum them up for me. And of course, we can represent it in this form, that GT is equal to the reward T, that the reward that I'm getting at state, starting state T. Reward T added by 1, added by 2, up to end. But meanwhile, we have a discount factor there too. What is the discount factor? It says, okay, we have a gamma term here that it's going increasing with the power and times to the reward. It says how important reward of the current state and future states are and how we can compare them together. So let me exemplify with very clear instance for you. So if I'm not in your life, you every day need to eat, right? And if you don't eat anything, you can save more money. But it's very important for you to eat now, otherwise you die, right? So the importance of the current reward is more important than what's happening when you get old. So you need to live happy, have a happy life now. But of course, important, the future is important too. This discount factor shows something similar to us. Says, okay, at the beginning, reward, the current, like robot is here, moves here, moves here. These parts are more important than 100 steps later. Because of that, we can control it by discount factor. So reward, immediate reward is very important. Then importance gets lower, gets lower, gets lower, gets lower. And how far we go, it almost vanishes. Apart from that we can control the amount of reward that we have by the definition of return. Also, what if we have a problem that the episode is infinity? we don't have finite episode that ends somewhere. We cannot say it's like prediction forever. It's in infinity loop, right? Then where this ends, you don't have this t that ends somewhere. So when you don't have that end, you can use this discount factor and kind of vanishing the end of the horizon. Just say a period of time for me is important. Some parts important. So we can use the gamma or discount factor over there too. So for example, usually you can use like 0.9, so like 90% of reward. Then when you get to power of the t, then it reduces the amount of the reward that we have during that. So this is the definition. We will see when we are going to use it. When I'm calling about the return, then you need to remember what's happening in the equations that we have. Any question? But most importantly, one of the critical, very, very critical elements of the reinforcement learning was value function. How we can formally represent it, let's have a look. We already know what it is now so far, but we usually show it with VS, value of the state. And the definition is expected return for starting from state S, or prediction of future rewards for state in case of multiple run. So that it's a little bit different from GT. Why? Let's have a look here. Also, we have another name. In reinforcement learning, when you're learning, when you're studying on the internet, you will face with a couple of terms, very confusing. Another name for the value function or value is known as state value function. Also, this state has definition. You will see soon, because we have only state here, because we can have action too. I will now explain it. So far we have state value function, and it looks like this. The value of S, what does it mean? So I'm in a state and I want to give some value. How good this state is? Value was saying that for me. The value of S is equal to expected reward of GT given by STS. So this GT, what was the GT? Was return. That return was discounted reward of future, all the states that the agent can have. Right? You may say, oh, so I'm RT, I don't know, what are these? So robot didn't run it yet, how we can get it? If you have policy, that policy indicates what is it. Just small explanation. So let's say we have random. At the beginning, robot doesn't know, everything is random. Like I'm here, turn left, right. I'm here as agent, turn left, right, I don't know, I don't care. This G represents what happens if I'm there in 100 steps based on the policy that we have also. I can a little bit clarify there. But then later value says expected return of the that value. That if I show it in detail, you can see that the immediate reward added by discounted reward in future. What is the key difference of the return and this value that we can say, okay, if you look at here, if you remember, I explained it already. So we are in the state S, we run policy pi, and we go S prime, and continue up to we get to the G, the return. And this one, for example, indicates one of these, the other one of these, one of these. And value can be, in simplest form, the average of those that shows us the value of S. If I get average of different runs, I can say, okay, the value of S is the one value that I'm considering. So that we can say value of S is the long-term value of state S that indicates how good each state is. Then what's the Q value? Now, we came to the point that I said here we have state value function, and the second name, there is a reason to call it as a state value. The reason is that we can have not only per each state indicating a value, from this state I maybe can do 100 different actions. If I want to say, okay, per each one of the possible actions at the state that I am, what is the value, then we call it as Q value. It is like more detailed. Instead of saying I am here, what is the value, I am saying I am here, what is the value if I from here go to the next, to the left, go to the forward, go to the right, go to the back. Per each one of them I can say I have separate value, and it is called as Q value. And we call it as action value function this time, instead of calling state value. So because it directly says, okay, what is the value of state, but here says action of the value, the value of the action actually. Sometimes you may hear, you may study in some research papers as expected utility ether. You may see, okay, it's written expected utility is blah blah. So it means that expected utility as action value function that we have over there, and it is known as Q value or Q of the state action. Is it clear? These are the most fundamental parts of reinforcement learning. We are going to use this a lot. If you have any problem, please clarify. Okay, how we can write its equation? We can say Q of SA is equal to expected GT, given by this time not only state but also action too. Per each state, what is the action? Then that's equal to expected reward, the same term, but again here I indicated by action that I'm choosing to. So it means that not only future states are important, but the chosen action per each state are important too. And finally, what can I do? We will see very nice equations to how to update this Q. Different algorithms have different techniques. The simplest form to understand it for now, get average. Average of expected GT. Expected GT, what was it? All the steps, discounted rewards. That I get 1 over n GT and the average of all rewards. Clear? Any question? Okay. So next term that we have in reinforcement learning, we are going to use it a lot again, is optimal policy. Optimal policy, we usually show it as pi star S, says, okay, what is the optimal policy per each one of the states? Let's say I know if I'm going to solve a problem that is path planning from here to the end of corner of the class that we have, I know that the optimal answer here in this state is left. Here in this state is forward. That's the optimal policy. And of course, we are going to solve the problems with reinforcement learning, ideally to achieve it. If you can find this pi star S, that's like great. We did great job. So the best possible actions, policy for that state. What is the optimal value? Here, we say what is the policy for state. Policy was turning left, right. actually kind of specifying the action also that we will see here. And here we say what is the value, best value that we can get if we are in some specific state. Just some evaluation value. So we can represent it V star S, or we can represent it as V pi star S. And also I've seen some other forms of representation, because when you are studying the algorithms on the internet, you should be familiar with to understand what's going on in the terms of the equations that you are studying. It says the best possible value for that state. And also, what is the optimal Q value is the same, but here the value, here we just only the value, here we have the value per action, the best value per action. Simply, all the definitions are same, we just can consider it as best. Here, what is the best value if I turn right? What is the best value if I go forward? Per each one of them, I have best value. Clear? So when time comes, we're gonna use these. Now, we want to define the optimal value functions. And if we want to say that, okay, how we can define the optimal value functions, we have two important terms. One is optimal state value function. Second value is optimal action value function. So optimal state value functions can be represented as V star S is equal to maximum of the pi of the maximum of the policy among the all policies of the value of the policy S. So what is the maximum value of the all possible values of the S that we can have? If we get the max, we can have V star S, and it is optimal state value function we call formally. And same thing for the action value. For action value, you again will face with it a lot. When we refer to talk about the action value function, we are meaning getting the maximum of the value of the pi per state and action, and we call it as here Q star of the S and A. Because as we define, that's very famous and well known to call it as Q value and Q of the state action. So if I want to bring out the key important element that I explained to you, when I'm talking about Q value, I'm referring to state and action. When I'm talking about the value, basically I'm talking about the value, just only the value of the state, not just the actions. I'm excluding those. Right? So in reinforcement learning, of course, we have multiple algorithms in different perspectives that we will see. But also we have two kinds of tasks generally. One is prediction task, and second is control task. So with prediction task, we say goal is to evaluate policy by estimating state value or Q value of the running actions on the policy that we have. What does it mean? It means that you have problem, and for that problem you have policy. You have policy already. You don't want to find it. Then prediction task says, okay, what is the evaluation of the policy? Or estimating the state value of the Q value or value itself. We call it as prediction task, so that you will see in next chapter, a chapter after next chapter, that you will see that we are going to say, okay, we solved the problem, we know the policy, and this policy, let's evaluate first the policy, how well that policy is doing. So we call it prediction task, and second task is the control task. In control task, we don't know the policy, and we want to find it by collecting the maximum of reward and indicate, okay, what is the each one of the actions per each state that I'm gonna take. So that in control task, we are intending to find policy. In prediction task, we are evaluating the policy. You may say, okay, why we have it? First of all, to understand second part better. Also, we have a couple of techniques and couple of problems that we need to have prediction task. And we will introduce some, and also in the book that I gave to you, you can study more to see what's going on. What are the tabular solution methods? Another definition in reinforcement learning, another class of the algorithms that we have. So the state value or Q value that are declared right now can be shown in form of tables if our algorithm is going to algorithm is going to represent the Q values or state values in form of tables, like per each state, what's the action that we have? Like I can define tables, and I can say, okay, ST is like, let me SA, B, C. So these can be states, and these can be actions. If I can show it in form of table, we usually call it as tabular methods that we are going to start to learn what's going on there. Later on in future, in some point, we will see that, okay, we have some problems with this guy over here. Then we try to change it to something better. So the core idea of the reinforcement learning is in simplest form. The state and action space are small enough, not too small. Still, they are good enough to solve normal size problems, but when the problem is too big, we want to replace them with some estimations. So in these cases, mostly we can find the exact solutions with trying enough episodes that required, or something near to optimal solution, so that optimal value function and optimal policy can be found over there. Any question? Okay. So when I'm now talking about optimal policy, all the time I'm gonna use it up to end of semester. I suppose you know what does it mean. When I'm talking about optimal value function, I suppose you exactly know what's going on. Because if you don't imagine it, then you don't understand what I'm explaining. Be careful, as I mentioned to you last week. The fundamentals in reinforcement learning are more important than algorithms itself. If you know the basics, you can understand very complex one. But if you miss some of these, it is like very, very hard to understand what's happening. So we have some more definitions for tabular solution methods. They are fundamental class of methods for solving finite Markov decision problem. We have a chapter for Markov decision problem in reinforcement learning class, but when we have finite Markov decision process, it means that it terminates somewhere. It's not unlimited, and as I mentioned in discount factor, we can have unlimited form too. And the solutions for that, we can have dynamic programming. We will see some methods that are developing in mathematical form and requires they usually require complete and accurate model of the environment. What I'm mentioning is the transition probability. So for dynamic programming solutions, we need the transition probability of the environment. We will see many examples. Then we move to the Monte Carlo methods that they don't require the model, and we have temporal differences that here, if you want to like quickly have a glance what's going on, there is no model. and the state comparison is incremental. We are kind of, when moving among these states, incrementally we are going to evaluate. No worry about this. We talk about exactly what is going on with a couple of algorithms for each one of the methods that you can see here. So if I want to summarize this chapter that we end, we discussed what is the reinforcement learning, state action value model, some of the application examples we saw together. Then we formulated fundamentals of the reinforcement learning and introduced the two different fundamental or general classes for prediction and control. Then we discussed some of the general approaches